So hopefully everybody's got their Google Doc open here for the work lab, right? So we'll do our usual walkthrough of everything. Okay, pay close attention as I explain how the lab is going to work so that you can get the variables. Okay. So we're recording two things here in this lab. We're recording distance and force. Okay. The way the lab is going to be set up is we're going to have a rubber band, okay, so one of these, and it's going to be strung between the legs of two desks, okay, not the legs of the same desk. They're not going to stretch that far, okay. So put it between, so the best way to do this is to have the back leg of one desk next to like the front leg of another desk so you can get them really, really close together, right? The reason we want them really close together is when we start this lab, we just want the rubber band to be taut, okay? We don't want it to be stretched at the beginning. We want it just so that it's not slack, yeah? So they got to be pretty close together for that. And you will have to take the little tennis balls off the bottom of the legs you use and put them back on after. Okay, so you'll take those off and you'll wrap them around. You'll see that there's little feet, okay, and there's kind of a groove above the foot. Put the rubber band in the groove above the foot of both legs, okay? And that way you're nice and close to the floor, okay? Just taut. Now the diagram shows you grabbing both sides of the rubber band. We're not going to do it that way, okay? And the reason we're not going to do it that way is because somebody used the rubber bands and didn't put them back. And these rubber bands are not the same as the rubber bands I usually use. They're much stronger. So if we pull both sides, we won't get very far before we run out of stretching. Okay, so we just want to grab one side so we can stretch them fairly far. Okay, everybody with me there? Okay, that's not a source of error or anything. We're starting with this, so it's going to be the same all the way through. Okay, it's just different. So we're going to have those on there. You're going to have a meter stick on the floor. Okay, and the meter stick is going to be right, so the zero will be right where the rubber band is sitting. Okay, so the front edge, the edge that you're going to pull, right, is going to be right over top of the zero, okay, on the rubber band. So you're going to have to get over top of that and look down at it. Okay, don't look at it from the side. What might happen then? No, well, hopefully not. But I mean, if I look at something from an angle, do I get the same perspective as if I look at it from above? Okay, so I got to be consistent here, and every time I take a measurement, I need to be right over top of the ruler. Okay, I would even suggest it's not a bad idea. I'll try and find some tape to tape the ruler down so that it doesn't move. Okay, on. Then what you're going to do is you're going to attach the spring scale. That's these things. Okay, to the rubber band, the hook end, and you'll pull on this end. Okay, and you'll simply record the measurement on the spring scale. Now, here's how we're doing this. We are picking, as the experimenter, we are deciding what distances we are going to pull the rubber band to. Okay, so the distances are being determined by us, the experimenter, and we are going to record the responding force to those distances. Now, when I stretch a rubber band, I'm exerting a force through a distance. What am I doing? Work. Okay, so there may actually be more than one responding variable here. Okay? Now, as I was saying, when you're setting up this experiment, there are some things you need to make sure are going to be consistent. Okay? We wanted to tape down the ruler so it didn't move. We wanted to make sure we were right over top of the rubber band when we're taking our measurements. Okay? We want to make sure that we're pulling straight, okay, along the ruler. And we want to make sure that this is actually on the floor when we're pulling, so that we're not pulling up at an angle or down at an angle or anything like that. We want to pull straight along the floor. Okay? That gives us our best angle for measurement and our most consistent force. Okay? if your rubber band breaks during the lab, what do you need to do? Start over. Okay, here's why. Remember how I said we want to make sure that when we start this, our rubber band is just taut? If it breaks and you have to put another one in there, are you going to be absolutely certain you get it exactly the same as it was when you started? Which means it's no longer controlled and not the next pull wouldn't be valid compared to the others. Okay? Here's the other thing you need to make sure of, and this is why we want to do this in at least groups of 4. The desks must not move during the lab. If they move, more tension will be put, or less tension will be put into the rubber band, and any trial after that is not consistent or comparable to the trials before. So 2 members of the group, your job is to be dead weight. You need to sit in the desks and make sure the desks don't move, because if you do this alone, okay, the desks will move. When you pull on the rubber band, there's nobody sitting in them, the desks will move. Okay? And then you won't be able to get them back where they were. Right? I actually had to put stuff in the desks when I did this myself to make sure they didn't move. Okay? And I actually put circles on the floor. So I knew exactly where the feet were. In case they did move, I could put them right back where they were. Don't put circles on the floor. Okay? That was a big no-no. Probably shouldn't have done. Okay? So just make sure of that. Little things, thinking, you know, stuff you're controlling, possibly. Okay, everyone clear with the setup of the lab? Another thing we have to be mindful of, there are 2 types of spring scales. There are 2,000 gram scales, they're red, and there are 500 gram scales, they are green and useless. It is written on the box which one is in there. This one's a 500, you don't want that. This one's a 2,000. This is the one you want. If you grab a 500, this will be over on the first trial, because you'll max out the scale right away. Okay? Everybody with me there? Make sure you get a 2,000. Now, the other problem we have with this lab is the scales themselves. Okay? They are adjustable, first off, so this little tab here at the top can allow you to change where 0 is. You'll notice now the tab is not sitting on 0 on my scale. Okay, before you start the lab, you need to make sure that that is the case. Okay, just make sure that it's zeroed up by moving that little tab at the top. Second thing is, we want these to measure force. What are the units for force? Newtons. Here's what's on the scale: ounces and grams. Yeah, we were pretty disappointed when we got these. Okay, 2006, we moved into the school, had all brand new equipment. Mr. Dickey and I pull out this brand new boxes of scales and see the picture on the front that says newtons and grams. And then we open up the boxes and we see scales that have ounces and grams and say, excuse me, and they wouldn't take them back. They never got our business again. The customer is always right. And in this case, we actually were right. These are not the right scales. They're like, yes, they are, but like the boxes are fine. Scales are not. Anyway, it's not a hard conversion. Okay? It's not a hard conversion to take it from grams to newtons. Okay? So, all you have to do, okay, is divide whatever the grams is by 100, and you've got your newtons. Okay? So if it reads on the scale 200 grams, that's 2 newtons. Okay, 400 grams, 4 newtons. Easy? Yeah. Okay. Now, the distances that we want to pull to, they may be a bit different because these rubber bands are stronger. So I'm thinking we're probably going to need to do this 1 centimeter at a time rather than skipping, because I don't think these ones will pull 15 centimeters. Okay? They're a lot stronger than our old ones. Yeah. Okay. So what we're going to do instead, and you can fill this in on your chart right now. Okay. So we're not going to use those numbers. Okay. So you're going to need to change these numbers here. We're going to have 0, obviously, okay? And then let's go with 2, 4, 6, and 8. Okay, so 0.02, 0.04, 0.06, 0.08. Let's look at our hypothesis here. Okay, so in our hypothesis, we want to talk about, first off, what work is. Okay, so the if part of your hypothesis should be a definition of work. You can find that right in your notes, so that's easy. Okay, the and part, as always, will describe the experiments. Okay, a rubber band is stretched to specify distances while the force involved is recorded. Okay? In the then part, I want you to tell me how you'll calculate the work using the data you will get. Okay? And the data you will get is force and distance. So once you have your data, okay, that is you have this chart filled in, okay, and the forces are filled in here, then you're going to build your graph of force versus distance. Okay, and that should look like the one here. Notice the distance is on the x and force is on the y. That's really important. Okay, make sure it's built this way. Okay, do it in Google Sheets. Put a best fit line on there with a linear fit. Right? You're not going to need, you're not going to, well, you can get the equation for the line, put it on there. Okay, it doesn't hurt to have it. And then for the analysis and interpretation, I want you to calculate the area under your line on the graph. Okay, so very much like what you did in the Need for Speed lab, right? Look at what shapes you have. Okay, if you got a rectangle, triangle, or you just got a triangle, whatever. Okay, calculate the area under the line, because this is what you need to think about for question number 2. What does the area under this force distance graph represent? Remember, it's not going to represent displacement. That's already on this graph. Okay, the area under the line on every graph represents something different. So I want you to think about when you calculate this area, okay, what's on the base, what's on the height. Okay, so when you calculate that area, what are you calculating? Okay, put in the right units, all of that kind of stuff. Spoiler alert, probably something related to the lab. All right, then with your conclusion, copy and paste. Okay, were you able to calculate work? Okay, was there anything you may have done during the analysis that possibly did that? Okay, and why? And then your sources of error. Okay, so 2 sources of error and the ways that you could possibly fix them. All right, questions from you guys there? All right, so this lab report's not going to take you too long to do. It's pretty straightforward. Okay. Come up and send one person up. When we're doing this, everybody has to be masked up because your faces are going to be close together. Okay, so we got to make sure that we're doing it that way. Groups of 4. Okay, and I will get some tape here so you can tape your meter sticks to the floor so they don't move. Okay, and get her done. Okay, guys, just in case you've forgotten how to do the graph here, okay, your data is probably going to look a little different than mine because this is the data for the thin rubber band where you have the thick ones. Okay, so I'm just highlighting that whole table, copying it. Make sure there are no units in the boxes, just in the top, because if you have letters in with the numbers, Google gets confused. Okay, bring it over to a Google Sheet, just make one. All right, so now they're in there. Now I can insert my chart. Okay, and I get a nice linear graph. Everything's already set on there. I might just want to change that. work lab or something like that in there. Okay, and get my test fit line. And get an equation on there, not that I'll need it, but it's there. Okay, you can see that most of the points are pretty much on the line. We got one that's a little above, one that's a little below. Yours probably looks something like that too. Okay, they're probably not going to be all exactly on the line, but it should look something like that. If your last point is way out, like it's much higher, it probably just means that you got beyond the true elastic range of the rubber band, and it stops being a linear. It stops being a linear increase and starts going exponential when you get past the actual elastic range. Did anyone have that problem? Okay. All right, so you're all good. Okay, just build your graph and then copy and paste it over into your lab report right here where it says insert graph here. Right, then you're good to go for your calculations.